In today's video lecture, we are going to see about the instruction set of PIC microcontroller. Fine. So as we have seen in 85 and 86, we do have instruction sets for data transfer, arithmetic operations, logical operations, then branch instructions, program control instructions, and then some machine control instructions also we have seen. So as of there, we also going to see such instructions for data transferring, arithmetic and logical operations, then branch instructions and machine control instructions. So with that, along with these instructions, specific type of instruction sets are also there. So what is that? In the sense, bit manipulation instructions, that is a special type here. So we will see each of these instruction set individually. Fine. So the instruction sets of PIC microcontroller are, first thing is bit manipulation instructions, move instructions, which is nothing but your data transfer instruction that we see in 85 and 86. Then arithmetic and logical operations for addition, subtraction, and then for logical and or XOR. Then the program control instructions, nothing but your machine control instructions. Okay. So other than these type of instructions, some special instructions are also there, so which will falls under miscellaneous instructions. Fine. So first we will see about bit manipulation instruction. So from name itself you can know that bit manipulation, in the sense you are going to manipulate a bit. Okay. So manipulate in the sense operating on, changing, so that is called as manipulation. So you are going to manipulate a bit of a particular register. That kind of instructions are called as bit manipulation instructions. So the first instruction in bit manipulation is BCF F, B. Okay. So here the F represents a file register. Okay. So file register, in the sense, yesterday itself we have seen about register file structure of PIC microcontroller. So in that they have given general purpose registers and special purpose registers. So this general purpose register will point out to the RAM memory, and special purpose registers are also there, I have told you yesterday itself. So it is of IO port registers and control registers. Fine. So we can use these kind of registers in this instruction. Okay. So the RAM memory registers are mentioned by the name or by its port number in the instruction. Okay. So then there is no specific name for those registers. A programmer by himself can name it each and every location, memory location, by himself in its application. Fine. So the special purpose register, the already name has been given, like FSR, INDF, interrupt control register, INTCON, port A. Port A is nothing but port A special register. Fine. So those kind of registers are called special purpose register. Fine. So here F is nothing but the file registers. It can be a general purpose or special purpose register. Fine. So comma B, this B represents the bit number of that particular register. So what this BCF will do is, this instruction will clear this particular bit's value belong to this F register. Fine. So clears bit B of file register F. So that's the explanation for BCF. So we will see an example now. So BCF status comma 05. So here the status is a register. Fine. So what we are supposed to do is, in this 8-bit register, we are supposed to clear this . So we are supposed to clear this 5th bit. So that's the meaning for this. We are supposed to clear the 5th bit of status register. Fine. So I have taken an example. Before executing this instruction, status register is having the value of A7. So A7, in the sense, this is the value for A7, right? So now the 5th bit is 1 here. Okay. So after executing this instruction, we are supposed to clear this 5th bit. So then what will become? 0, 1, this 1 will become 0 now. Okay. So what's the value now? 8, 7. So after executing this instruction, status register will have the value of 8, 7. Fine. So what this instruction will do, it will clear the particular bit of the file register and store the value again in the file register. Fine. So on the next instruction is BSF F comma B. So this is similar to this, but here we are clearing that particular bit, here we are setting the particular bit of F register. Fine. So we will see an example, BSF intcon comma 7. So this intcon is nothing but a special purpose register. Okay, its name is interrupt control register. Okay, so what we are supposed to do here, so in the interrupt control register we have to set the 7th bit. So this S is for 7. So before executing this instruction, intcon is having the value of 0B, which is nothing but 0B. Okay. So what we are supposed to do, we are supposed to set the 7th bit. 7th bit is nothing but this last bit. So when we set this, what value will be there in intcon register? 10001011, which is nothing but 8B. So now 8B will be stored in interrupt control register. So these two are the bit manipulation instructions. Fine. So the second set of instruction is move instructions, which is nothing but data transfer instructions. So here we will use these move instructions to move a data from one register to another register. Fine. Okay. So the first instruction is move F comma D. Here your F is the source and D is destination. So this is quite different from the instruction set of 85 and 86. So in 85 and 86, first we will mention the destination, then only we will mention the source. But here in PIC, first we are supposed to mention the source and then the destination. Fine. So move F comma D. So what this instruction will do is, it will move the content of F register to the D register. Fine. Okay. So here I have taken an example, move FSR comma W. So FSR is a special purpose register, W is also a special purpose register. So FSR is file select register. We have seen in the previous video lecture what for it, what's the purpose of it and all. Then W is a working register. So what will happen here is, the value from the FSR will be stored in working register. Okay. So before executing this instruction, FSR is having the value of 00 and working register is having value of 98. So what will happen after executing this instruction? This will move the value of FSR into working register. So working register will have the value 00. So FSR is also will have the value 00. Okay. Keep the point in your mind. Here the value is copied from one register to another. It is not cut pasted. It is copy paste. Fine. The next instruction is MOV LV LWK. So what this instruction is, so if you want to move an immediate value to a register, we can use this instruction. So this instruction will move the literal value, L for literal, okay, literal in the sense immediate. Move the literal value into the working register, W is for working. So this literal value we will mention in the instruction itself. Fine. So this will load the literal value K into the W register. So by executing this instruction, the status register will not be affected. So this status register is nothing but the flag register. This we have discussed in the previous video lecture itself. Fine. So for example, I have taken this instruction move LW5A, which means that, so working register, after executing this instruction, working register will have the value of 5A. Fine. So here this value, literal value is moved to the working register. The next instruction is move WF F. Okay. So here this F represents the file register and W represents the working register. When we use this instruction, the value in the working register will be stored in the file register. That's the meaning for this instruction. So by executing this instruction, the status register will not be affected. Okay. So for example, I have taken this instruction move WF port B. So this port B is a special purpose register meant for only port B. Fine. So before executing this instruction, port B is having the value of 0, 5 and working register is having the value of 9B. So when we execute this instruction, what it will do? It will move the value of working register into the port B register. So what the value in port B now? It will be 9B. So and working register will have the same value 9B. Okay. So that's the explanation for move WF. Okay. Move VF will move the value from file register to the working register. So move LW will move the literal value to the working register. Move WF will move the working register value into a file register. So these are all the data transfer instruction. And the next instruction that we are going to see is swap instruction. Fine. So swap is nothing but exchange. So exchange operation is called as swap. So in 85 we do have exchange instruction that will exchange only between the HL and DE. So later in 86 we do have exchange instruction that is used to exchange value between any of the register that we mentioned in the instruction. So here this exchange instruction is called as swap instruction. Fine. So swap F comma D. So this instruction will swap the lower and the higher number of the particular F register that is mentioned in the instruction. Fine. So this will not affect the status register. So for example, I have taken swap F on comma 1. So here on is nothing but the file register. Okay. So the name that we give to a particular register of the RAM memory. So this is depending upon the programmer, whatever name he wants to give to that particular register, he can give it other than the name that has been given to the special purpose registers. Fine. So for example, if I say that in a RAM memory I want to use the register at the location 81H. Fine. So I can use that register in the instruction as 81H, or else I can name that 81H as on register. Fine. On or other name that I wish to give. Fine. So now what I have to do, I have to swap the value in the on register. Fine. So on register, for example, I'm saying it's having the value of F4. So when we execute this instruction, what will it do? It will swap between the lower number and the higher number. So number is nothing but 4 bits. So what it will happen? It will swap between the same register. The lower number value 4 will be given to the higher number. So and the higher number value will be stored in the lower number. So after executing this instruction, our on register will have the value of 4F. So this is the explanation for swap instruction. And the next instruction is clear instruction, CLRF. So what this instruction will do is it will clear the content of F register. Fine. So for example, I am taking port A register. Okay, clear of port A. So if port A is having the value of 96 before executing, so when we execute this instruction, the port A will have 00. Okay. So the content of this register will be cleared. Fine. Next is CLRW. Okay. So what here is, here we have cleared this file register and here we can clear the working register. So before executing this instruction, your working register will have some value. After executing this instruction CLRW, the working register will be stored with the value of 00. Fine. So the next set of instructions that we are going to see is arithmetic instructions. Okay. The first instruction in arithmetic is addition. So what here we are doing is add LWK. So this instruction will add the literal value K with the working register and store the result in working register. Fine. So the literal value can be in the range of 00 to FF. So since this is an 8-bit controller, we are supposed to use only 8-bit values, which means that this controller is able to access only 8-bit values. Fine. So we are going to add this literal value with the working register, and again we are storing the result in working register. Fine. So this instruction will affect the carry, digit carry and 0 bit of status register. Fine. So I have taken an example instruction, add LW 15. So here 15 is the literal value. Okay, before executing this instruction, working register is having the value of 10. So when I execute this instruction, what will happen? This will add, that means the 10 will be added with the literal value. As a result, we will get 15. So this will be stored again in the working register. So now the working register will have the value of 25. Okay, so that is for add LWK, to add the literal value with working register, and result will be stored in the working register. Then the second instruction is add WF F comma D. So what this instruction will do is, it will add the F register value with the working register, and the result will be stored in the destination mentioned in the instruction. Fine. So it will add working register with flag register, so the result will be stored in destination register. So this instruction will affect the carry, digit carry, and 0 bit of status register. Fine. So there are two ways to mention the destination. So that is the D part. If you want to store your result again in the working register, in the destination part you have to mention the value 0. So if you want to store the result into the file register, you have to mention the destination field as 1. Okay. So as of here, so if you mention 0 in this part, which means that you are storing the result in working register. 1 in the sense you are storing the result in F register, that means the file register mentioned in the instruction. Okay. So here I have taken an example, add WF 05 comma 0. Okay. So this 05 is nothing but address of file register. So what here it will do is, it will add the working register value with the register, this is a register. Okay. So this is the value in the register 05, and store the result in the destination. Here I have mentioned this as 0 in the sense the result will be stored in the working register again. Fine. So before executing this instruction, working register is having the value of 17, and the memory location 05 is having the value of 02. So by executing this instruction, what will happen? The 17 will be added with 02. So the result will be 19, and this will be again stored in the working register. So after executing this instruction, working register will have the value of 19. Fine. So the next instruction is subtraction, sub LWK. So what here it will do is, it is same as add LW. This will subtract the literal value by working register and store the result in working register. Okay. So I have taken an example, sub LW02. So before executing this instruction, working register is having the value of 01. So by executing this instruction, what will happen? 2, the literal value is subtracted. This 1 will be subtracted from 02, and the result you will have 1. So that will be stored in working register. Okay. So after executing, working register will have the value of 01. Fine. So this is for sub LW. So here the working register is subtracted from the literal value. Don't forget that. Okay. So the next instruction is SUB WF F comma D. So this is similar to add WF, but here is the working register is subtracted from the file register, and result will be stored in destination. So it depends on the value 0 and 1 of this destination field. So here I have taken an example, SUB WF 02 comma 0. So this 02 is nothing but the address of file register, right? So this will subtract the 02 value, the content of 02 minus this working register. Fine. So before executing this instruction, the address of the register is having the value 5. Okay, working register is having the value 1. So result you will have 04. So here at the destination field 0 has been given. So the result will be stored in working register. Okay. So for example, if I have mentioned 1 here in this field, again this value 4 will be given to 02. Okay, 02 register. Fine. So the next set of instructions that we are going to see is logical instructions. So logical operations you already know, AND, OR, XOR, so all these operations will come under logical instructions, right? So here as of the addition also, if you want to in addition and subtraction we do have added the working register value with the literal value and the working register value with the file register value. So like the arithmetic, in logical also we do have that. If you want to AND the working register with literal, we are having an instruction for that. If you want to AND the working register content with the file register content, so for that also we do have an instruction. Fine. So we will see it one by one. The first instruction is AND LWK, which means that working register is ANDed with literal value and the result will be stored in working register. Fine. So I have taken an example, AND LW 5F. So this 5F is ANDed with the working register. Now the working register value is A3. Okay. So what's the value of 5? So the operation that we have mentioned is AND. So if you want to perform AND operation, so 1 1 is 1, 1 1 is 1, 1 0 0, 0 1 0. So this you know already. So now the value is 0 3. Fine. So what will happen? We have already told that the result will be stored in working register. Now the working register will have the value of 0 3. So our next set of instruction is AND with file register, working register and file register, and result will be stored in destination. Fine. So here I have mentioned 1, don't forget that. The example is INDWF FSR. So here the FSR value will be ANDed with the W register. Since I have mentioned 1, the result will be stored in FSR. So before executing the instruction, W is having 1 7, so FSR is having C2. So the binary equivalent for that is so this is for C and this one is for 2. So now I am supposed to perform AND operation. So 1 0 0 1 1 1 0 0 0 0 0 0. So this is what the result. Okay. So 0 2. So since I have mentioned 1, the value will be stored in the file register. The file register mentioned in the instruction is FSR. So now the FSR is updated with the value 0 2. Fine. So in the same way we will mention our instruction and then the XR instruction, this XR. Fine. Okay. So LW in the sense the W register will be AR'd with the literal value, result again will be stored in the working register. So in IOR WF F comma D. So the working register is AR'd with the file register and result will be stored in the destination. So in this example, the destination is mentioned as 0. So the result register, okay, the result will register, the content of result register is AR'd with the content of working register and result will be stored again in the working register since 0 has been mentioned. The same way for XR. So LW in the sense literal value XR'd with the W, right? And then W XR W F comma D. So F is XR'd with the W and the result will be stored in destination. So here see to this example, the register F register is REG and the destination field as 1, which means that the working register is ANDed with REG and the result again will be stored in the REG. Okay. So the next instruction is COMP F comma D. So COMP is nothing but complement. So what this instruction will do is it will complement the content of F register and stores the result in destination. So here as an example, complement 1 comma 0, the 1 is nothing but the address of the specific general purpose register and 0 is the destination field, which means that after complementing the value of this register, the value will be stored in working register. Fine. So before executing the instruction, one register is having the value of 1 3, so which is nothing but this one. Okay. So when we perform complement, each and every bit will be inversed. So 1 will become 0, 0 will become 1. So this value will be stored in 1 register. So after executing this instruction, fine. And the next instruction is DEC F comma D. So DEC is nothing but decrement. So this instruction will decrement the content of F register by 1 and stores the result in destination. So see here, decrement the content of F register by 1 and stored in D register. Okay. So I have taken an example DCF. CNT is nothing but the address of our general purpose register, and then the destination field as 1. So before executing, CNT is having the value of 02 in the sense. So the 02 is decremented by 1, and again the result will be 1. This will be stored in CNT since I have mentioned the field as 1. Okay. After executing, CNT will have the value of 0, 1. So next instruction is INCF F comma D, which is nothing but this will increment the F register by 1 and stores the result in destination. So see the example here, INCF SAT comma 1. So SAT is nothing but address of the register. So if before executing the instruction, if SAT is having the value of FE, after executing this instruction, so plus 1 we will have FF, right, as a result. So since we have mentioned the destination field as 1, so this FF will be stored in SAT again. Fine. So the next logical instruction is RLF F comma D. So RLF is nothing but rotate left F register through carry. We should involve carry here. So after rotating the instruction based on the destination field, your result will be stored. Okay. So if this is your 0th bit and this is your 7th bit, the it will be shifted 0 to 1, 1 to 2, likewise 6 to 7. The 7th bit will be given to the carry and the carry bit is given to the 0th bit. Fine. So here for example, I have taken an instruction RLF REG comma 1. Don't remember that, I have given as 1. So before executing this instruction, REG is having the value of FF, right. So 1 1 1 1 1 1 1 1 and carry is having the value of 0. So after executing this, what will happen? This 1 will be transferred here, right. So assume this is your first bit. So this 1 will be transferred here. So like this, your values will be transferred. Okay. So now the 7th bit will move to the carry will have the 1 now. So then the carry bit 0 is given to 0th bit. So this is given to 0th bit. So what's the value now? Carry is having the value of 1 and this value is FE. Since I have given 1 here in the destination, this value will be stored in REG register. Okay, this is what this rotate left will happen. And the next instruction is rotate right through carry. Carry should be involved here. So what we have to rotate? We are supposed to rotate this file register. So this is your 0th bit and this is your 7th bit in the sense. So how this rotation will happen? We will take the same example that we have discussed previously with the same values. Okay, quite different value. FE is not E. F7 is given here. Fine. So if we rotate right in this direction, so what will happen? The carry is given to the 7th bit, so which is nothing but 0, then 7 to 6, so 6 to 5. So like this will be shifted. So this will be given to 3 will be given to 2, no? So and then this value is given to carry now. So now carry will have the value of 1. So what this value? 7. B and carry is having the value of this. So this 7B will be stored in REG register since I have given 1 here. So if I have given 0 in the sense, this 7B will be stored in working register. Fine. So the next set of instructions that we are going to see is program control instructions. Fine. So these instructions are used to control the program execution and transfer the program control from one memory location to the another memory location. Okay. So that's the purpose of program control instruction. So the first instruction that we are going to see is BTF SS F comma B. So what this instruction will do is, so this instruction will check the bit number B of F register. Okay, so it will first check to it. If that bit is set, which means that if that bit is 1, then this instruction will skip the following instruction, jump on to the another instruction. Okay, so if that bit is not set, which means that if that bit is 0, then it will execute the next instruction. Fine. So see here, check bit B of F register and skip the next instruction if it is set. Okay, so this instruction will not affect the status register. We will see an example now. Fine. So these are all the instruction, and HIF is nothing but the address of this particular instruction. Okay, so BTFSS status comma 2, this instruction is stored in the address H. Okay, so see here, so what this instruction is supposed to do, it will check the bit number 2 of status register. Okay, so before executing this instruction, your program counter will have the address of this instruction, which is nothing but address H. Fine. So after executing this instruction, if my status bit second bit value is 1, so this will skip the instruction of the address I and it will move on to instruction addressed by the address J. Okay, so if that bit is 1 in the sense, so your program control is transferred to J address of J instruction. Okay, so that is PC will be moved with the value of address of J, right. So if that bit is not set, which means if it is 0 in the sense, so this will execute the instruction in the ith address. So the PC will have the address value of I. Okay, so can you able to understand it now? So this instruction will check the particular bit of F register. If it is set, means it will skip the immediate instruction, jump on to the other instruction. If not, it will execute the immediate instruction. So the next instruction that we are going to see is BTF-SC F comma B. So what the previous instruction does, it will check to the bit number B of F register and skip if it is set. So what this instruction will do is, it will check to the same say it will check in the same way, it will check to the bit number B of file register F and skip if that particular bit is clear in the sense if it is 0. Fine. So as I told you, check bit number B of file register and skip if the next skip to the next instruction if it is clear. Fine. So I have taken an example. So this represents the address location. These are all the instructions. So BTF-SC port A comma 3. So this instruction will check the bit number 3 of port A. Okay, and skip if the port A third bit is 0. Okay, otherwise it won't skip. So this will skip to jth instruction if bit number 3 is 0. So it will not, it will execute the same instruction. Fine. So before executing this instruction, PC will have this address of this instruction, that is H will be there in PC. Okay, so after executing this instruction, if bit number is 0, 3 is 0, so then it should skip on to J. So then address of J will be there in PC if third bit is 0. So if not the case, which means that if the third bit is 1, it will execute the ith instruction. So I address will be there in PC. Fine. The next instruction is INCF SZ F comma D. So what this instruction will do is, so INC in the sense increment, F means file register. So this instruction will increment the file register to 1 and store the result in destination register, and S in the sense skip. So and then it will skip if the result is 0, Z means 0. Okay, so can you able to understand what's happening now? This instruction will increment the content of the register that we have mentioned in the instruction by 1 and check whether the content of that particular register has become 0 or not. So if that content has become 0, it will skip the immediate instruction and jump on to another instruction. So if not, if the content is not 0, then it will execute the very next instruction. Fine. So here we can see an example. So these are all the instructions, and here and CONT are the address of that particular line. Okay, don't get confused. Instead of mentioning the address 1500 and 1600, I have mentioned it with the name. That means with the label I have mentioned it. Fine. So what I'm doing here, so this instruction address is labeled with here. So INCF is S is at CNT 1. So what this instruction will do is, so this will increment the value of CNT register, the content of CNT register by 1, and result will be stored in CNT register. So why CNT? So here I have mentioned it as 1. So after incrementing, this instruction will check the content of CNT. So if the CNT value has become 0, it will jump on, it won't jump. If the CNT value is 0, it will jump on to the next instruction, which is nothing but here. Okay. So if this is not 0 in the sense, it will execute the go to instruction. Fine. So before executing, the PC will have the value of here, right? This instruction's address, it will be here. So after executing, CNT is equal to CNT plus 1. We are supposed to increment it. So after incrementing, if the content has become 0, this will be skip on to this label CONT. So otherwise, it will have the address, immediate address of here. So after this immediate, we'll having this instruction. So this instruction address we can find from plus 1 of here. So that is mentioned here. Fine. And the next instruction is DECF SZ F comma D. So this is the operation is same as in increment instruction, but that what's happening here is, in increment we are incrementing the content of the file register. Here we are decrementing the content of the file register, and again we are checking whether the file register content has become 0 or not. So if it is 0, it will skip on to the another address location. If not, it will execute the immediate instruction. Fine. So that's what I mentioned here. So here F is decremented by 1, okay, stored in the destination, and skip if the result is 0. So see here the same example, instead of increment I have mentioned as decrement. Okay. So before executing this instruction, your PC will have the address location of here, right? So after executing, which means that after decrementing, if my content has become 0, okay, so this will jump on to the label CONT. So or else it will execute the go to here instruction. So that address we can fetch it like, so the immediate address only, no, so I have added plus 1 to get this address location. Fine. Okay. So on the next instruction is call K. So K is nothing but address of a subroutine. So if you want to execute a set of program which is stored in another location, we can use this call instruction. So those kind of programs are called as subroutines. If you want to execute a subroutine which is stored in another memory location, you can use this call instruction to jump from one memory location to the another. Okay. So what this call instruction it will do is call the subroutine program stored in the memory location K. Okay. So while calling a subroutine, which is nothing but calling a program which is in another location, which is not similar to the main program that we are executing now, right? So for that we are supposed to save the status of our main program in the stack. So for that what we have to do, so when we are executing the subroutine program, after finishing executing it, we are supposed to return to the main program where we have stopped. So for that we are supposed to store the address location where we have stopped the execution. So for that we are supposed to store the program counter value into the stack and the status registers values into the stack. So then only when only the controller is supposed to call that particular address subroutine program. Fine. So before jumping or before calling it, so the PC value plus 1, we will have some memory location, no, that is stored in the top of the stack. Fine. And then the call address should be transferred to the program counter, right? No. So the call address we have mentioned in the instruction. So that value is stored in the program counter. So that too from 0 to 10th bit, that is 11 bits. 11 bits value has been transferred to PC counter. So we already discussed in the previous video lecture. So the PIC microcontroller might have the 2K capacity of memory or 4K capacity of memory. Okay, so this controller is supposed to know that where it's supposed to access that subroutine, whether in the 2K or 4K of memory. So if it is 2K memory or 4K memory, that is decided by the PC latch register. So that we have discussed in the previous lecture. Okay, that we are using here in this set of instruction. Okay, so 0 to 11 bit, so 0 to 10, which is 11 bit, will tell you whether I am accessing the memory location, particular memory location. So assume that as 2K, 4K. Okay, so the bit number 3 and 4 will define you whether I am accessing 2K or 4K. So this third and fourth bit of PC latch is given to program counter. Fine. So when the 11th bit is 0, means I am accessing. Okay, 0 to 10 is given by the address from the instruction, right? So the if my 11th bit, which is from the PC latch, is 0, I am accessing the 2K memory. If the 11th bit value is 1, which means that I am accessing 4K memory. That's the meaning here. Okay, so here I have taken an example, call then. So then is nothing but, okay, I will give an example with the address location. Fine. Okay, so the address of this call instruction is 6500 and I am calling a subroutine which is stored in the memory location 5000. Okay, so before executing the instruction, PC will have the address value 5600. So while it executing this instruction, as I have already told you, the PC plus 1 value is supposed to store in the top of the stack. So then top of the stack will have the address of 5600 plus 1, which is nothing but 5601 will be stored in the top of stack, and PC will have the address now as 5000. Okay, so this is what will happen when we execute call instruction. Okay, then we discuss about go to K. So what this instruction will do is, this is an unconditional branch. So why we call it as unconditional? In the sense, we didn't mention any condition to jump on to the memory location K. Okay, so what this instruction will do is, previously in call instruction we have stored the status of the current program in the stack. So when you execute the go to instruction, we are not supposed to do such, we don't need to do such transferring of the status into the stack. We can, the controller can just jump to the address location mentioned in the instruction. So because why the status are not stored, in the sense, these go to instructions are short term jumps. Okay, short range of jump. Okay, so it will jump to the same segment with the memory capacity of 2K, sorry, not 2K. So 2 or 4 bytes of memory. If you want to jump from 2 or 4 bytes of memory later than the one that we have mentioned in the instruction, we can go for this go to address. So since it's jumping with the near memory locations, there is no need to save the status of the program in the stack. Okay, so but the PC value has been should be changed to the kth address, and that the PC latch will tell you whether you are accessing 2K or 4K of memory. Fine. So the next I have given an example here. Okay, so take an example of, so this instruction address is 5000 and go to 5010. Okay, so when your PC is executing this instruction, before executing it, PC is having the value of 5000, right? So after executing this, PC will have the value of 5010, so which is nothing but here. So this program will jump to this location, no need to save the status. And next instruction is RETFIE, which is nothing but return from interrupt. Okay, so when an interrupt occurs, so what will happen? The interrupt subroutine will start to execute. So before executing the interrupt subroutine, the status of the program should be stored in the stack. Okay, so once the subroutine has finished its execution, the controller is supposed to jump on to the main program where it stops its execution, right? So before jumping, what the controller is supposed to do? It has to restore the values that it has stored in the stack. So if we want to return to the main program, this kind of instruction is used when we are executing the ISR. Fine. Okay, that instruction is called as return from interrupt. at the end of your ISR this instruction to be mentioned. This will help the controller to jump on to the main program by retrieving the data from the stack. Okay. So when you are executing this instruction, the top of the stack value is retrieved to PC and your global interrupt enable has to become 1. Okay. So when we are discussing the feature, we have discussed that this series of PIC microcontroller is having 12 independent interrupt sources, right? So if you want to enable these 12 interrupt sources, we are having a common enable bit called global interrupt enable. So if that bit is 1, then only the interrupt program, then only the interrupts will be recognized by the controller. If that global interrupt is 0, even when the interrupts are occurred, these will not be recognized. Fine. So once the global interrupt is enabled and an interrupt has been occurred, before it starts to execute the ISR, the controller will make this global interrupt enable to 0, which means that it will disable the global interrupt to avoid the interruption of the ISR that has to be executed further. Okay. So when it returns back from the ISR, the global interrupt enable is enabled to see whether other interrupts has been occurred or not. Fine. So and the status register is not affected by this. Okay. So as I have already told you, when you interrupt from the subroutine to the main program, right? So you should know where you have stopped in the main program. So for that you have to retrieve the value from the stack to PC and global interrupt enable should be made 1. Okay. So our next instruction is return with loading the literal value into the working register. Okay. So which is nothing but you are suppose when you are executing a program subroutine, okay, when you are executing a subroutine, at the end of that if you mention this instruction as I have mentioned here RET-LW88. So what this instruction will do is it will return to the main program. Okay, it will return to the main program from the subroutine. Okay, before returning it will write the value of working register as 88. Okay, fine. So by returning it will retrieve the top of the stack to the program counter. So then only we will know where we have stopped in the main program. Okay. So before executing the instruction, the working register is having the value 9A. So after executing this 88 will be loaded into the working register and top of the stack is given to PC. Fine. So next instruction is just return. Okay. So the return that we have discussed before are one return is for return from interrupt subroutine INTFIE. Okay. And next is to return with the literal value to the working register. So this return is without any conditions. So these instruction is used to return from the subroutine program. So before returning a top of the stack value is given to the PC, then only we will know where we have stopped in the main program. Okay. So these are all the machine control instructions. So the next set of instructions are miscellaneous instructions. So these instructions does not fall any of the categories that we have discussed before. The first one is NOP. NOP in the sense no operation. When your controller executes this instruction, it does not perform any operation and will remain idle. Okay, your controller will remain idle. And the next instruction is sleep instruction. Okay. So if you want to, when your controller is not performing any operation and it is remaining idle without performing any operation, right? So then you can put your controller into the sleep mode. So when you see your laptop and PCs, if you're not working with your laptop and PC, after some minutes, it will go to the sleep mode, right? So that's the same case here. Okay. To reduce the power, we will use this sleep mode. Okay. If you give the instruction sleep, then your controller will go to the sleep mode, that is power down mode. Okay. So when you use this instruction, automatically the PD bar bit, do you remember, status register, one of the bit will become 0 and timeout bit will become 1. Okay. And the next instruction is CLR WDT. So WDT is nothing but watchdog timer. Okay, the function of watchdog timer we have discussed in the previous video lecture. If you want to clear that watchdog timer, which means that if you want to disable the watchdog timer, you can use this instruction. Okay, so these are all the instruction set of PIC microcontroller. In general, instruction set only we have discussed in the video lecture. Fine.